Okay, good afternoon. Myself Anil Kumar. I'm here to start the third lecture under GNSS and its application course. Third lecture, if you see, as I mentioned, I will cover on GNSS measurements and positioning techniques. Before this lecture, I've already talked about introduction to GNSS, and the second was satellite-based navigation systems. So there, yesterday I talked about different type of satellite-based navigation systems. It was global as well as regional systems in full details. And today, let me start on GNSS measurements techniques and positioning techniques. So if you talk about GPS signals or GNSS other navigation signals, these satellites continuously transmit the signals, and which contains lot of information. This information, if you see in the context of Navistar based satellites, they carries the carrier frequencies, that is phase information of the signal, course acquisition, CA code, precise code, and satellite message. Using these information, we can adopt two type of measurements from the GPS receiver depending upon its capability. The first one is code measurement, which uses time information, and second is phase information, that is called carrier measurement sometimes. And third information is satellite message. It has different names, ephemeris or almanac, which from where we extract lot of information about the satellite. So if you see the description of these signal components, specifically for the code measurement, it has each satellite has a unique pseudo-random code. The CA code is the basics for civilian GPS use. It is very common to be used by the civilian users, open to the civilian users worldwide. And the second pseudo-random code is called P code or precise code. It is basically restricted. It is not open to the civilian users. It is only restricted to the defense people of USA. If you talk about Navistar satellites, same way for other global and regional navigation satellites, there are two categories, defense and civilian. So defense is defense of that same country, and civilian can be any person in the worldwide. So that is the category. You can see the two categories, the data is available. It repeats. If you talk about the CA code, for the Navistar satellite, it repeats on a 7-day cycle, modulates both on L1 and L2 carriers at 10 megahertz. So from this, how we do measurements, we calculate range, direct distance from a satellite to the ground where we are doing measurements, and that range is direct distance is basically calculated through signal velocity, that is V, velocity of light, multiplied by time of signal traveled from satellite to ground. So it is V is equal to, range is equal to V multiplied by time traveled by the signal. So through code measurement, or we can understand the very basic concept how this measurement works, and to get our coordinates. Suppose this is Earth and we want this point to be measured. So we are locking suppose 3 satellites, satellite 1, 2 and 3. So here we have to measure row 1, row 2, row 3. We want X, Y and Z coordinates of this point on the ground. So here we can say it is X1, Y1, Z1 coordinates of the first satellite. So if you see range 1 as an equidistant distance, it is under root x1 minus x chi square plus y1 minus y chi square plus z1 minus z So by this formula, we can get the range. But as I told you in my previous lecture, there is a quartz clock here. In the GPS receiver, there is a quartz clock. And here there is an atomic clock, which is giving time up to 10 to the power minus 9 second atomic clock, and this giving time up to minus 10 to the power minus 3 seconds. So both clocks has to be synchronized. So there is synchronization error. Plus, you will see one more variable, time synchronization error. So there are 4 variables unknown, x1, y1 and z1 plus sigma. Sorry, x, y and z coordinates of the ground plus epsilon. This same way for rho 2, we will have equation plus epsilon and rho 3. Now you can see there are 4 unknowns. So we require 4 satellite. We require 4th equation also, rho 4. So this concludes that for 3D observation, we require 4 satellites. And for 2D observation, we require 3 satellites. This is the conclusion, right? So I have already spoken number of times. For 3D observation, we require minimum 4 satellites. Why it is? Because there are 4 unknown variables, x, y, z, and this epsilon. And once we know range, so this range we calculate while using the formula rho is equal to v multiplied by time. So v is the velocity of the satellite and time is the signal time from satellite to the ground. So once we know rho, we can put in each equation, and for each satellite we can find out rho. Then we can put it in the each equation to solve x, y, z, and epsilon. This way the code measurement is works to get the coordinates. Now second method is, as I mentioned, is carrier measurement or phase measurement. So here the range is not calculated. As I mentioned, range is equal to v multiplied by time. This is the code measurement technique where we are using time of the signal to get our range. But here we calculate phase. Phi is the phase is equal to range plus lambda wavelength of the signal plus n is ambiguity. It is also called number of cycles present in the signal. So from here we can find out rho, range of the signal, is equal to phi minus lambda n. Phi is a linear unit, even though phi be used as an angular form, but here it is used as a linear value, and then wavelength and n is number of cycles present in the signal. You can see one cycle. So here this is one cycle. Same way, if it is like this, then it is 1.5. It is like this, then it's n is equal to 2. This is first cycle and then second cycle. So here n is read from the signal up to fraction part. The last cycle may not be the full cycle. Whatever its fraction part is read. So that has to be read very critically. So here carrier phase measurement is a measurement of range between a satellite and the receiver expressed in units of cycles of the carrier frequency. This measurement can be made with very high precision of the order of millimeter, and that's why when we do measurements through carrier measurement, we get very high accuracy in our data. But the whole number of cycles between satellite and receiver is not measurable. That's why we have to, the system takes time to resolve the fraction part of that cycle. And that is called, once the system is able to read number of cycles, it is called ambiguity resolved. That means the system is able to read the number of cycles present in the signal. A good analogy is to imagine a measuring tape extending from satellite to the receiver that has numbered markers every 1 millimeter. That's the meaning of cycles. Unfortunately, however, the numbering scheme returns to 0 with every wavelength approximately 20 centimeter for GPS L1 frequency. This allows us to measure the measure the range very precisely, but with ambiguity in the number of whole carrier cycles, but we have to read up to fraction part. The number of subtitles must be considered when generating these measurements in a receiver. A third information what we get from GPS signal is called satellite message. The technical term we use is called ephemeris. This is broadcasted on the website or on the portal of that particular GPS Navistar or particular GPS systems. From that agency portal, we can see the ephemeris every 15 days approximately. For USA based, every 15 days we can download the ephemeris, which is very precisely defined. This contains information on week number, satellite accuracy, health, age of the data, satellite clock corrections, coefficients and orbital parameters. From orbital parameters, we calculate the known coordinates of the satellite, valid 2 hours before and 2 hours after time of ephemeris. The toe can be thought of as when the data was computed from the GNSS control segment. That is the time of availability used for real-time satellite coordinates computation, which is required in position computation. Second type of satellite message is called almanac. This almanac we can download from GPS receiver. This contains less accurate orbital information than ephemeris, valid for a period of around 90 days, used to speed up time to first fix 15 seconds compared to not having almanac stored. So almanac information we can download from GPS receiver itself, but ephemeris we require to be downloaded from a portal of that agency, which is handling the Navistar satellite data. So here just I have given you the idea about the measurement techniques. In the hardware, we can adopt 2 types of measurement techniques. The first is code measurement technique, second is carrier measurement technique, and third data is satellite message. Satellite message gives the health of the satellite, age of the satellite, its coordinates, its current position, and all these informations are used in code measurement as well as in carrier measurement. The carrier measurement is more accurate approach than code measurement. According to the hardware in the setting, we can select which type of solution it will provide, but automatically it goes for code measurement or carrier measurement depending upon the configuration of the hardware. If the hardware is having capability only for code, it will not use carrier information. But if it has the if it has the capability to use the carrier information, so then it will work for carrier. But if it is not able to resolve the ambiguity, then automatically it will switch to code measurement technique. So when we are purchasing the GPS receiver, we have to see we want code measurement instrument or we want carrier measurement instrument. Specifically, the geodetic GPS receivers are built to be capable for carrier measurement. If you see like RTK, GNSS, we'll see later also. Like here, you can see different GPS in the area. So there is one base station on the ground, second base station, third base station, fourth base station. All base stations are calculating the coordinates. They are then calculating the corrections with respect to the actual coordinates, and these corrections are sent to the master control station. From there, these corrections are sent through internet, through a ground tower or through GSAT satellite, from where these corrections are transmitted to the wider area, so that the concerned user can apply these corrections. Now, second portion of this lecture is called positioning techniques. So first one, I told you two type of measurement techniques we can adopt in the field as per the hardware requirement: code measurement or carrier measurement. Carrier is also called phase measurement. Now, using these measurement techniques in the field, we can adopt a different type of positioning techniques depending upon our requirement, and accordingly we can achieve the different level of accuracy from our GPS receiver. So if you see these positioning techniques through GPS or through GNSS, we can have single point positioning technique, we can have relative positioning technique, we can have static positioning techniques, kinematic positioning technique, and in relative positioning we may have two subcategories called real-time positioning technique or post-mission positioning technique. So we will see these positioning techniques one by one. If you talk about single point positioning, and then we can compare it with the relative positioning also. The positioning with GPS may take the form of single point positioning or relative positioning. So here if you see, this is an example of single point positioning. So what is happening, it is locking the few number of satellites, minimum 4 for 3D and minimum 3 for 2D. And we have a on the ground GPS receiver, which is just locking the available satellites and getting the coordinates. So it is not referring any other information on the ground. That's why it is called single point positioning. But I have added one more word, static. Since at this point, the GPS receiver is static, so we can say it is single point static positioning. In single point positioning, coordinates of a receiver at an unknown points are calculated with respect to the Earth reference frame by using the known positions of the GPS signals being tracked. That means these satellites are the known point to me. Whenever these are tracked, according using these satellites, we get our own coordinates on the ground. This is also called, the single point positioning is also called absolute positioning or just point positioning. We are not referring any other information on the ground. Just using these informations, we are calculating our own coordinates. Then second approach, what I mentioned, the relative positioning. Through this example, you can understand the meaning of relative positioning. What is happening here, in relative positioning, we require minimum 2 GPS receivers. One is kept at point number 2 and second is kept at point number 3. So here this point number 2 is called control unit or base unit, and the machine which is kept at point number 3 is called rover. So what is the objective? Objective here is we should get the coordinates of ship with higher accuracy. So for that, we can adopt relative positioning to improve the accuracy of rover. So what we have done, the base unit is kept at a lighthouse. Why? Because at the lighthouse is a known point. So we know the actual coordinates of the lighthouse, X naught, Y naught, and Z naught. Now at the base unit, it is continuously doing observation, say every 1 second. So every 1 second it is doing observation. We can define this rate of observation 1 second, 2 second, 0.5 second in the GPS receiver. Suppose by default I have taken 1 second. So every 1 second it is giving coordinates at point number 2. So every 1 second, the moment I get coordinates, using that coordinates I compare with the x naught, y naught and z naught, and then I can find out every 1 second what is the error in x, error in y and error in z. So we can find out these errors every 1 second. Now if you see the rover, rover is also doing observation and its observation rate is same 1 second. So every 1 second we are getting the rover coordinates also. So if the error at point number 2 and at point number 3 is common, so we can apply this error from point number 2 to point number 3 using this pink line. So pink line is basically representing the data transmission from base to rover through beacon. So beacon is an electronics device. At point number 2, beacon is working as a transmitter. At point number 3, beacon is working as a receiver. So receiver is receiving the corrections. That's called corrections, means it is receiving the errors from point number 2 to point number 3. The question comes, how we can apply the error which is at point number 2 to point number 3. We can only apply the error once the error is common at point number 2 and at point number 3. How we can make the error is common? First thing is both GPS should lock common satellites. So with the help of mask angle, it is possible we can make both GPS receiver lock common satellite. Second thing, both GPS should do observation at same time. So if we keep the observation rate same, so I have kept 1 second. So in that case, both will do observation at same time. Third condition is the environmental condition at point number 2 and at point number 3 should remain same. So it is only possible when we maintain the distance between point number 2 and point number 3 maximum to be 20 kilometers. Up to 20 kilometers it is assumed the environmental condition are same. So with these three conditions, first one, both are locking common satellite. Second one, both are doing observation at same time. Third is environmental condition at point number 2 and point number 3 is same. So then we can say that error at point number 2 is common to error at point number 3. Then we can apply the error from point number 2 to point number 3. So that is called relative. So relative means that the accuracy of point number 3 is improved with respect to point number 2. So here you can see the title relative. So with respect to 2, accuracy of point number 3 is improved. That's why it is relative. Kinematic, rover is moving. The base, the ship is moving. That's why it's kinematic. Real time. Real time means you can see there's a beacon at point number 2 and there is a which is working as a transmitter, and beacon at point number 3 is working as a receiver. So real time corrections are applied from point number 2 to point number 3. So 3 words has been used. You can see one more stage here. It is relative. So here you can see one base unit is kept in the forest. It is connected with the beacon which is working as a transmitter. Put it on a tall tower. It is transmitting the error in the larger area. So here at the rover you can see beacon which is working as a receiver to receive the corrections, which is connected with the base with the rover. So here this is a rover and base is here. This is B and this is R. So here also it is fulfilling the first condition. Both are locking common satellite. Both are doing observation at same time, and the distance between base and rover is not very high. It is less than 20 kilometers. So the error at base and rover is common. So that's why it is relative. Static. So you can see rover is static in this case. It is not moving. And real time. So you can see real time. There is a beacon which is working as transmitter to receiver. So it is applying the corrections. So this is relative, static, real-time positioning techniques. Third type of positioning techniques can be static or kinematic. So GPS positioning may also be categorized as static or kinematic. In static positioning, a GPS receiver is required to be stationary, whereas in kinematic positioning, a receiver it collects the GPS data while it is moving. So here you can see the GPS receiver is kept on a car and then it is moving. So it is kinematic observation. And here the GPS is static, standing at a point and doing observation. That's why it's called static positioning. Now, then you can see real time and post mission. In the real time, the base is kept at a lighthouse and rover is somewhere in some other in the field, and both are communicating through radio link, through beacon. Here is transmitter and here it is receiver. So it is transmitting the error from base to rover. So it is real time positioning technique, relative real time. And here, if we don't have beacon, we don't require beacon to use. So what we can do, whole day base is working and whole day rover is working. In the evening, we can download the data of base and rover in a laptop or in a PC. We can use post-processing software. Post-processing software will apply corrections from base to rover. So here you can see it is post-processing concept. Overall, you can have kinematic single point positioning. This is least accurate data. More accurate data is static single point positioning. Then you have kinematic relative positioning. Kinematic rover is moving and base is always static. Here is static relative positioning. Rover is static and base is also static. So if you draw N like this, the accuracy is improving. If you follow the path of this N, accuracy is improving. This is least accurate and this is most accurate observation technique. Static and kinematic positioning technique. So this is the two components I have explained. One is your in today's lecture measurement techniques, and second is positioning techniques. In measurement, as per the hardware hardware capability, we can use code measurement technique only, because hardware can do code measurement technique. If the hardware can do phase measurement technique or carrier measurement technique, by default it is capable for code measurement technique also. So while doing observation, if the hardware is able to resolve the ambiguity, that means the hardware is able to calculate the number of cycles present in the signal, then it will go for carrier measurement technique. Otherwise it will go for automatically switch to code measurement technique. Sometimes when you are moving and doing observation and the cycle gets slipped, so it will go for code measurement technique. Otherwise it will go for carrier measurement technique. These carrier measurement technique capabilities are generally kept in geodetic GPS receivers, which are single or dual frequency, where you want accuracy of say 1 centimeter or a millimeter or fraction of millimeter accuracy, which is geodetic dual frequency. So there you can go for carrier measurement. Otherwise 80% jobs from GPS can be done, or by GNSS can be done through code measurement technique. Like if you see a mobile phone, so here in this, the GNSS chip which is there is basically using the code measurement technique, not the carrier one, because carrier one is more bulky. It has so many other capabilities so that it can resolve the ambiguity and so forth. So this is all about today's lecture. Daily basis, I'm just covering very focused lecture, not very large content, small content, so that you basically, my objective is you understand the basics of GPS and GNSS with different aspects, and later on you can go in more deep. So very basic component should be clear to you. Today is the third lecture, and tomorrow, if you see the schedule, I'll be talking about GNSS receivers and GNSS errors. So there you will see different type of GPS receivers, GNSS receivers, and different type of GNSS errors which are there. And then you will get an idea how these errors, what these errors are, and how to minimize these errors in the GNSS or GPS receivers while doing observation. So let's take the questions. Thank you all for listening.